Hi, and welcome to another edition of Easy Theory. So today we're going to be doing 4 examples of the pumping lemma for context-free languages to show that these 4 languages right here are all not context-free. So we went over the pumping lemma for context-free languages proof in the last video. So let's actually use it to show that some languages are not context-free. The method for showing that a certain language is not context-free is very similar to the one that we do for regular languages. So actually I'll put my advice, or at least the steps that we'll do. So the first step is to assume, I'll move it up a little more, assume that L is a CFL, just like with regular languages. And then what we'll do is we'll show that there exists a pumping constant P for L, exactly the same as before. Then we need to pick some W string in L with the length of W being at least P. And that will allow us to assume that there exists a parse tree of the correct size in terms of the number of leaves at the bottom of the tree. Then what we'll do is to look at all decompositions of W into the 5 parts, which is now where it's different than the regular version, where it had 3, this one has 5, such that we have those famous 3 conditions. I'll write them as A, B, and C this time. That u v to the I, x, y to the I, z is, oh no, that's not the condition. Excuse me. So there are 2 conditions, and we use the third one to get the contradiction, which is the length of vy is at least 1. So one of the 2 is non-empty. And B, the length of vxy whole thing, so including the x part, is at most p characters. And as the final trick in my magic act, we got to find one value of I. So find one I such that u v to the I, x, y to the I, z is not in L. Because the pumping lemma says that it will always be in L for every choice of I. If we can find one that doesn't, then the language cannot have the right property. So that will show that it's not context-free. Okay, so let's do the first one, which is A to the n, B to the n, C to the n, where n is at least 0. You would think that this might be context-free, but the intuition is, if we have, say, a PDA, for example, then the idea is, well, we push on the A's and then pop off the B's in tandem. The problem is that the number of C's has to match exactly the number of A's and B's individually. So they have to be exactly matching. Okay, so what do we actually do here? So just like in my instructions, we assume, I better give this language a name. So let's call it L1. So let's assume that L1 is a CFL. Then what we know from that is that there exists a pumping, I'm only going to write it this time, pumping constant P for L1. So then now we got to pick a string that's in the language. So it has an A's followed by B's followed by C's and the same number of each. And it has to have length at least P. So one thing that you might try is to pick A to the P over 3, B to the P over 3, C to the P over 3. Well, that has length at least P. There are several problems with it, but one thing is that P might not be a multiple of 3, so this is not an integer, but you can fix that by, say, taking the ceiling of these if you wanted to, and that has length at least P. But there's an easier one uh, to write down and to actually consider, which is a to the p, b to the p, c to the p. It's actually better because remember the vxy part could have length p exactly. The reason why we do that, why we do this instead, is that the vxy part, which is all consecutive, can either be in the A part, or the B part, or the C part, because it can technically be anywhere in the string. It can touch the A's and the B's simultaneously. It can straddle between the A's and the B's, or it can straddle between the B's and the C's, but it can't hit the A's, B's, and C's at the same time, which is going to be key. So let me actually make this a little more compact. So we know that this string is in the language and of length of at least p. That doesn't guarantee it'll work, but it's a good starting point. Oops, wrong one. All right, so now we need to look at all decompositions. So look at all decompositions into those 5 pieces, u, v, x, y, z. Well, I don't know, according to the rules, I should say. According, and I'll only write it this time, according to rules. Well, we know that the vxy part doesn't have to be at the beginning. It could be anywhere. So let's see. Suppose that, so let's look at a particular set of cases. I'm not going to write u is equal to some set of characters, v is equal to this, x is equal to this, because it's just not necessary. And it's just going to complicate things way too much. So let's look at, I'm going to call it case 1, which is that v and y are, actually I'll write it this way, v and y only contain a's. So if we look at what the string looks like, actually I'll change this to red. So we have a bunch of a's, then b's, then c's, like this. So if v and y only contain a's, then that means that the v part is somewhere in here, the x part is in here, the y part is in here. Oh god, that was terrible. There, that's a little better. The z part is the rest, and the u part is at the beginning. That's just what this case is saying. There are obviously other cases. So if we pump up, if we insert another copy of v and y in, I don't know whether v or y is non-empty, but I know one of them is. So if we pump up to, let's just say I equal 2, any value of I actually other than 0 works here, then what will happen is that we will have more A's than we started with, because one of these two is non-empty, and so we're going to be putting more A's into the string, but we're not going to be adding more B's or C's. So then this tells us that the resulting thing, which is 2 copies of V and Y, because we're putting another copy in, has more A's than B's or C's. And that automatically disqualifies it from being in the language, right? Because the language has exactly the same number of A's, B's, and C's. All right, what if we had a different case, 2, and this is actually multiple cases at once. V and Y only contain B's or only contain C's. Well, actually, the same logic will apply. It's just the conclusion's a little different, but the same contradiction is reached. Because if they're only, say, within the B part, then by pumping up, we're putting more B's into the string, which means, and no A's, no C's. So therefore, we have more B's in that case than A's or C's. And if it was only within the C part over here, then if we put more A's into the string, more C's into the string, we're not going to insert any A's or B's, and so it's not in the language anymore. So what about the other possibility, which is case 3, that v and y only contain a's and b's. So let's visualize what this looks like. So if I have a bunch of a's here, b and c. Actually, you can show that in this case, both of these have to be non-empty if we weren't in the other cases, but that's not important. So the v part is over here because it's before the y part, although that doesn't matter. The x part is going to be somewhere here. It may cross into the b's, we don't know for sure. But I know that the y part is in the b's only. And I know this because that's what I assumed. And of course, vxy together can be at most p characters, and each of these ranges has exactly p characters. So it can't be the case that we touch one of the a's and one of the c's at the same time, because it has to cross this gap of p characters, and it can't have more than p characters. So the v part, I'm assuming here, y is over here. So if I pump up again, in this case, then I'm going to be putting more a's into the string, more b's into the string, maybe the same number, we don't know, but the number of c's is not touched. And so the number of a's, b's, and c's cannot be the same. This actually shows right here, if we just ignore the c's and just only have a's and b's, we show that this is context-free. Because this decomposition, if I have the same number of a's and b's for the v and the y part here, we can actually pump up and still have the number of a's and b's. But because of these c's over here, that allows us to show that this cannot be pumped in this particular case. And then if we look at the other possibility, which is that v and y only contain b's and c's. Not sure if you can hear the garbage truck out here, but the logic is exactly the same. If the v part was in the b's and the y part was in the c's, then we're never touching those a's at the beginning. And so the number of a's, b's, and c's cannot all be the same number. And so we get exactly the same conclusion. But the important thing is we can't have any other case, because if we, the only possibility of another case being is that we have A's, B's, and C's, but we just discussed that that can't possibly happen because we made these gaps so big, these consecutive parts of the string. They have P characters each. That's why I was saying P over 3, that idea doesn't, it won't work as well, because in that case you could have A's, B's, and C's at the same time. But by making these big enough, we can show that we can actually not have to worry about that possibility. And so because of this, in all cases, we were able to pump out of the language. We have a different value of I possibly in each time, and we'll see an example of this, but we were able to pump out of the language in every possible case. So that shows that L1 is not a CFL. All right, so let's go on to the next language, which is very similar. I'm going to call it L2, which is A to the I, B to the J, C to the K, where not that they have to have the exact same exponent, but I is less than or equal to J, less than or equal to K. And actually the proof is slightly different, but it's very, very similar. So we gotta start as usual. We're gonna suppose that L2 is in fact a CFL. And I'm just gonna shorthand this. There exists a pumping constant P for L2, this language. And of course, just like now, we need to pick some string that's in the language and long enough, at least P in length. So I'm actually going to choose W to be exactly the same exponent in all cases. And that's okay because we have a less than or equal to for the I and J and K here. Ooh, I put K here. That's not what I wanted. I wanted P. And why is this a good idea? Why not put like +1 or +2 here or whatever? The key is that we want to break these conditions. So my advice here is to pick strings that are right on the edge of not being in the language anymore. If I have one fewer B or one fewer C than this, then I get out of the language entirely, which is exactly how we'll actually prove this, by the way. Okay, so how are we going to prove this? So we're going to, again, look at all decompositions. I'm going to shorthand it again. U, V, X, Y, Z. So we got to look at all decompositions. We got to break them up into cases. So let's assume that V and Y are only in the A's right here. So the V and Y are only in this first section. Then if I pump up, we're putting more A's into the string, which means that we're going to break this condition right here. So we're going to have more A's, so that means I gets bigger than J, because I and J started out exactly the same number. So this tells us that there are more A's than B's or C's. Okay, which immediately shows that you leave the language. That immediately leaves the language. Case 2, V and Y are only in the B part. So if it's in the B part, then what we can actually do is you can actually pump either direction, either up or down. Why? Because if I pump up, that'll put more B's into the string, which means we'll have more B's than C's because they're only in the B part. If I pump down, take some B's out of the string, then I'm going to have more A's than B's, even though I didn't touch the A's because they had the same number to start with. So, I should have said, if we pump to I equal to 2. And in fact, any other value other than higher than 2 also works. So pump here to I equal to 2, just as an example. Then here, for what will happen is that we'll get more B's than C's, which breaks the condition of being in the language. What about the case of where V and Y are only in the C's? So this argument of pumping up I claim won't work. Why? Because if I put more C's into the string, then that will just only make this condition more and more true. It'll just make K bigger, but that's okay because as long as it's bigger than or equal to J. So what we'll do instead is we'll pump down. Pump down to I equal to 0. You can only pump down to I equal 0. Then what will happen is, because we have exactly the same number, at least one C will be deleted, right? Because one of the two pump pieces is non-empty. It can't be the case that both of them are empty. So that means at least one of the C's is deleted, which means that we'll have more B's than C's. And so that will leave the language. So again, here we'll have more B's than C's. It's the same conclusion as the previous thing, but gotten in a different way. Okay, well, what about the other cases of where it straddles between two segments? It can't have all three segments, again, because of this gap of P characters, which were all B's. So case 4 is where V and Y only have A's and B's. Okay, so let's try to visualize this. So we have a bunch of A's here, B's, C's. And just like before in the first one, we showed, let's just say that the V part's here and the Y part's here. So it could be that they have the exact same number. So if I pump up or down the V and the Y together, remember they have to have the same exponent, then I could have exactly the same number of A's and B's, which actually shows that if you restrict this problem to 2 characters instead of 3, you can actually keep this to be a context-free language. Or that's actually a way to show that it is. But suppose, we'll look at the case where we have 3. Well, if I want to break the condition, I want to have fewer C's than either B's or A's. So the only way of doing that is to have more B's than C's because I'm not touching the C's at all. So the key here is to pump up to I equal to 2, or higher, it doesn't matter. Then here we'll have more A's or B's. I don't know which one it is because I don't know whether I am having A's or B's here because I don't know which one of these two is non-empty. I could break it up into some sub cases, but it's enough to handle it here because I need one of the 2 segments to have more than the number of C's, which I know it will be in this case. So whichever one it is, it will break the condition that the C's have the most number in this case. And then finally, in case 5, we'll have V and Y only have B's and C's. So now we got to treat this one a little different because if the V part's in here and the Y part's over here, then what we need to break the condition in a different way. We want to have fewer B's or C's than A's because I'm not touching the A's in this case. So we need to do the exact opposite thing. We need to pump down to I equal to 0. So whichever one of these V or Y is non-empty, I have no idea which, one of the 2 is going, when we pump down, we'll take one B or C with it, or maybe both. In either case, we're going to have more A's than B's or C's, whichever one is the case, and that'll break the condition to be in the language. So we'll have fewer B's or C's, I have no idea which, than A's. And those are all the possibilities because, again, I can't have the V and the Y part hitting the A's, B's, and C's at the same time. And so that tells us that L2 is not a CFL. Okay? All right, let's do the third one. So the third one is very commonly, there's a lot of misconceptions about it. So this is the language WW, so the exact same string twice, where W is any possible binary string. Note that if it was just zeros and not 0 1s, then this language would be regular, and so therefore is context-free, because it would be all the even length strings. So whatever string we pick here has to have both 0s and 1s, because if I just have zeros, then at every point I'm just going to have an even length string, and this language only has even length strings. In fact, it has all even length strings that have the same 2 halves. And if you have only zeros or only 1s, and it's even length, the 2 halves must be the same. So I must have zeros and 1s in whatever string that I pick here. So let's do an example. Let's do this. So let's suppose that L3 is a CFL. Then we know that there exists a pumping constant P for L3. So then now we got to pick a string. Let's choose 0 to the P. So it has to have at least P characters, and I must have zeros and ones in order for this to even possibly work. And I also must have the two halves being exactly the same string, because that's what this condition is telling me. So if I pick this string, 0 to the P1, and I must have the two halves being the same, so 0 to the P to the 1, it turns out that we can actually find a decomposition that will always stay in the language, which is really weird. So here's what the decomposition looks like. So if I have a bunch of zeros, a single one, then a bunch of zeros, and a single one after that, then what I can actually do is this decomposition. So I'm going to put 1, 0 here. And what I'm going to have is that the U part is right here. The V is a single character, the 0. The X part is the 1 right here. The Y is just the single 0. And the rest of it is the Z part. And that's a valid decomposition because as long as P is at least 3, then we can always pump this string. Why? Because if I'm putting an additional copy or deleting a copy of V and Y at the same time, then I'm putting a 0 on both ends. I'm going to put a 0 in this set and a 0 in this set, and the two halves will be exactly the same length. And they will have the same number of zeros on both sides, and so therefore they are exactly the same. So unfortunately, I can't pick this string, but the idea is very good. The reason why this went wrong is that the V part was in one set of zeros, and the Y was in the other set of zeros. So if we can make the gap between the sets of zeros big enough, length P, then we can actually force it to only touch one set of zeros at a time, or one set of ones at a time. So what we'll pick instead is 0 to the P, 1 to the P, 0 to the P, 1 to the P. And this is, of course, of length at least P, and is exactly the same string on both halves. So this is the same as this, which is pretty nice. So we need to look at all decompositions. So look at all decompositions into U, V, X, Y, Z again. So let's see. We can actually handle this into 2 cases, believe it or not. Reduce it to 2 cases. You could handle every single possible case, but this is a lot easier. So what I'm going to do is I'm going to look at this string in 2 halves. I'm going to call this the left half, or the first half, and this is the right or the second half. So case 1 is that V and Y, actually I'm going to break it into 3 cases, are only in the first half. Okay, they're only over here. So let's try to visualize what this looks like. So we have a bunch of zeros at the beginning, then a bunch of ones, then a bunch of zeros, which is starting the second half, and then the set of ones at the end. So this is, so again, here is the midpoint of the string. And so V and Y are over here somewhere. So let's say V is here, Y is here. I don't really, this case is telling me that it doesn't really matter where V and Y are. As long as they're over entirely on one side, then that's okay. So let's see what happens. So it turns out that you can pump in either direction here. But let's visualize if we pumped up. Pumping down works very analogously. So let's visualize what happens. So what happens if we pump up to I equal to 2? Then what happens is we're putting more of V and Y into the string. So that tells us that in order to stay in the language, the two halves must be exactly the same, right? Um, and I'm not going to worry about whether we're putting in an even number of characters. If we put in an odd number, then the whole string's length is odd, and so it can't be have two halves that are exactly the same. But let's just assume, for example, that v and y contribute an even number of strings, but it won't actually matter. So the key is this. So we're going to look at the string again. So here's zeros, ones, zeros, ones. So what happened is, well, if we put more of the left stuff here, then if you think about it, the original midpoint of the string, which is right here, so this is the original midpoint, well, it must have moved somewhere because the string actually got longer. Or it changed length, that's what matters. It changed length so that it must have moved somewhere. If you think about it, there's more characters over here. So that means that then, or over here. So that means that this midpoint actually moved to the left because in order to have the two sides have exactly the same length. So that means that the new midpoint is over here somewhere. So this is the new midpoint. And here's the key idea. Because it moved, the right side here must start with a 1. Okay? And you can prove that, you can even prove more than that, but it's the right side starts with a 1, but the left side starts with a 0, which is a contradiction. So the right side starts with a 1, oops, and left starts with a 0. So that tells us that the two halves cannot possibly be the same because they start differently. And you can actually prove more than that, but that's enough to show that the resulting string can't possibly be in the language. And actually, the same logic works if we look at case 2, where v and y are only on the right side. Because if we pump up to I equal to 2, now in this case, there are more stuff on this side if we put more onto the right side, because that's where they are here. The original midpoint was here, but now the midpoint has to move this way. So that means that the left side ends with a 0, and the right side ends with a 1. I'm getting notifications. So let me write what happens here. So pump up to I equal to 2, then what happens is the left side ends in a 0 because the midpoint moved, and the right side ends in a 1. And so the two halves cannot possibly be equal to each other because they end differently. It's a very similar conclusion, but it's not the same conclusion, obviously. The first one is they started differently. Now in this case, they end differently. But now there's one other case, which is that v and y, what are called straddle the middle of the string, where the v is on one side, the y is on the other side. So don't ever forget to leave out one of these possible cases. So let's try to visualize what this looks like. So we got zeros, ones, zeros, ones. So in this case, this saying that the v part is here and the y part is in fact here. So what are we going to actually do here? Well, let's see what happens. Let's try to pump up again. It'll actually work. So let's pump up to I equal to 2. Then what happens is that you can actually show that if we're not in the first two cases, then both v and y are both non-empty in this case, although it won't actually matter. But we can show that they are non-empty. So let's just think they're non-empty. So v is non-empty, y is non-empty. If we pump up to I equal to 2, then that means we're putting more 1s here and more 0s here. So here's the key idea. If we put more 1s here, then that means that this set of 1s has to be identical to this set of 1s because they can't both be on the same side, unilaterally on the same side. And for that reason, this set of 1s cannot possibly be equal to this set of 1s because this originally had the same number as this, and we're putting more 1s into the string. Similarly, if we're putting more 0s in here, it can't be equal to this set of 0s, which we didn't touch. So here, just as an example, the number of 1s on the left side is not equal to the number of 1s on the right side. And similarly for 0s. Okay, and so that shows that this string cannot possibly be in the language because the two halves cannot possibly be the same because the number of one of the characters is not the same. Never mind whether it actually is in the right order, but they can't possibly be the same. Okay, so those are all possible cases because each of these ranges has p characters, so I can't hit 3 of the sections at the same time. And so in all cases, we have shown it to leave the language, and so L3 is not a CFL. All right, so now let's do one that's actually kind of really interesting. So we're going to hold an election. No current events are motivating this, by the way, just as a disclaimer. So we're holding an election here, and the string that we have is in the set A, B, C, D, whole thing star. So it's just a string of A's, B's, C's, and D's. And the set that we're interested in is the set of all strings W in this set, such that the number of C's, as an example, it could have been A's, B's, or D's, but it doesn't matter. The number of C's is more than the number of A's, B's, or D's. Okay, so the number of C's is more than the number of A's, B's, or D's here. Okay, this is what is called winning by plurality. So win by plurality. Can't spell plurality. Plurality. It's not majority because we're not requiring that the number of C's be at least 50% of the length of a string. What we're just saying is that the number of C's is bigger than the number of A's, B's, and D's. So C technically got the most votes. And so what this should tell you is that a context-free grammar or anything like a PDA or something cannot possibly have this language. And so we shouldn't use context-free grammars in elections. That's your PSA for the day. All right, so what I want to show is that this thing is not a CFL. So let's assume that L4 is a CFL. And what we'll do here is we are going to, we know that there exists a pumping length P for L4. So now we need to pick a string that's in the language and long enough. So remember my advice, which was to pick a string that's just barely in the language. And any small tweak is going to have it not be in the language anymore. So if we want the number C's just barely bigger than the number of A's, B's, or D's, then what I'm going to do is I'm going to have the string to be C to the P plus 1, A to the P, B to the P, D to the P. Okay. The A, B, and D order doesn't matter. In fact, the C order doesn't matter either, because remember, we can technically pump anywhere, but it's just, I like putting it at the beginning here. Okay, so what do we actually do here? So we gotta, again, look at all the possible cases. So look at all decompositions into U, V, X, Y, and Z. And so we want to have it so that C doesn't win by plurality anymore. It could be that one of the others wins by plurality, but we want C to not win by plurality. Okay, so what will happen? So let's look at some cases. So case 1 is V and Y are only in the C's. So since it's barely more, if I try to pump more into this, then what I'm going to get is more C's. And that's not going to ever leave the language. I want to leave the language. So here, what we need to do is to pump down to I equal to 0. So what will happen there is that, so then what we'll have is, actually I'll write it this way. So the number of C's, because we take at least 1 away, but it could be 1, the number of C's is less than or equal to the number of A's in particular. And so that clearly shows that C couldn't have gotten more votes than A did, because it's less than or equal to it. But if we think about V and Y being anywhere else, the A, B, and D are all symmetric to each other. So if we have a second case here, we can actually group a lot of possibilities together. V and Y are only in A's or only in B's or only in the D's. And so it's only, we call this uniform in that it is only one character. It doesn't have 2 different characters. So in those cases, let's just say example for the A's, then we want to have more A's than C's, or at least as many A's. So if we pump up to I equal to 2, if we pump down, then it won't work because we'll have fewer A's. But if we pump up, we'll get at least as many A's as C's because we're obviously putting at least one A into the string. So what we'll do here is we will pump up the jam to I equal to 2. So the number of A's, B's, or D's, I have no idea which one it is, but it's one of those, will be at least the number of C's, which allows us to actually leave the language. Okay, so now let's look at some of the more interesting cases. So, case 3. So let's see. If the V and the Y part are only within this right half, like they straddle the A's and the B's or the B's and the D's, it can't have all 3 for reasons we've discussed. So if it had A's or B's at the same time, so V and Y only have A's and B's, or B's and D's. So it's saying that it's within this right half, but it's between these, either between these 2 or between these 2. So in either case, all A and B and D are symmetric to each other, so it doesn't actually matter. So what we'll do then is we'll just pump up, just like before. I don't know which one will be inserted because I don't know whether V or Y is empty, but I know that if they're over here, then if I put more over to here, we're not having the number of C votes change. So the number of votes for one of the candidates over here will be at least as many as the number for C. So what we can do here is, just like the last one, we can pump up to I equal to 2. And so the number, and actually the conclusion is exactly the same. The number of A's, B's, or D's will be at least the number of C's, just like before. But just like before, I don't know which one of them is the case. It could be that 2 of them go up, but the important thing is that they beat C. Okay, so what do we actually do here? So the only other possibility, so case 4, is that V and Y only have C's and A's. Okay, so they only have C's or A's, and A's. And in fact, if it didn't hit one of the other cases, we know that it must have at least one occurrence of C and one occurrence of A. So what will happen is, what if we pumped down? So let's actually try to visualize this. So we have C's at the beginning, because that's how we design the string, then A's, then B's, then D's. So this is saying that the V part, which of course comes first, is in the C's, but the Y could have C's and A's. It doesn't actually matter. So let's just say that it has only A's, but it could have more. It could have some of the C's too. Here's the thing: if we pump down, then it could be that the number of C's and A's goes down, but we don't know which one for sure. But the key is the number of B's and D's doesn't change. And so because of that, one of these two will have more votes than C does, because we're taking at least one C away, which means that the number of B's and D's will be at least as many as the number of C's. So in this case, if we pump down to I equal to 0, then what will happen is either the number of B's is at least the number of C's, or the number of D's is at least. Oh, I forgot to put a number sign there. My mistake. So number of C's, number of C's. One of those two occurs. I have absolutely no idea which one, but I know one of the two will occur. And so in this case, C did not win by plurality, okay? One of B or D will, but I have no idea which one. And so we leave the language in that case. So finally, after all that, we have finally shown that L4 is not a context-free language, because we left the language in every possible case. So hopefully that was interesting. Leave questions about the pumping lemma for context-free languages down in the comments, or if you have any other interesting thoughts or problems about context-free languages and the pumping lemma down below. As always, please like and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support this channel further. And as always, I'll see you next time.